Welcome to this session. Till now we've seen, we've learnt about process, we have learned the process definition, and we have seen how the system can be modeled with the help of process states. Processes, we've seen processes can exist in a various states, and they can transit from one state to another, and these process states together, they can be used for modeling the computing system. And what we had seen there, we had seen a two-state process transition diagram. Then we saw that we found out certain shortcomings with a two-stage, then we extended it to a three-stage, five-stage, and seven-stage process transition diagram. In this lecture, what we are going to do is we are going to talk about most widely used variant of a process state transition model, that is process state transition diagram for a Unix system, which is a variant of a seven-state process transition diagram. Then further going forward, we would try to see how the process is organized inside the machine and how the process is managed by the operating system. So this is what we would try to cover in this particular session. So let us just recollect the previous session. We had talked about this particular diagram, that is a seven-state process state transition diagram. So we find that we have a new state where the process, when any process begins, it joins in a new state, and then from a new state it goes into a ready state at some point of a time, and then dispatcher dispatches the ready process. It goes to the running stage, and from running it can go to the exit once it terminates, or in case if it is in running stage, it might make a request for IO service, so it will go and get blocked on a IOs and it will wait for an event to occur, that is a completion of IO, and when event occurs it will go to the ready state. And at times it is also possible that when the process is in blocked state, for a want of more amount of resources, the blocked process could be swapped out of memory and it can go into a blocked suspended state, and from a blocked suspended it can go to ready suspended and return back to the ready state. So this is the process state transition diagram we have seen. Most of the current day existing operating systems, they use some kind of a variant of this state transition diagram. We will just try to see the Unix process state transition diagram. So if we here we find that the diagram which is depicted is a Unix process state transition diagram. So we have a state known as a created. So whenever process is forked, process would use a fork system call to create a process. So a new process always begins at the stage what we call as a created state, and if there is enough memory in the system, then it goes to ready to run in memory. So this is something similar to a ready state in the seven-state transition diagram. If while it is in when the process is forked, if there is not enough memory, then this process goes ready to run in swapped state. So this is something similar to ready suspended state in case of a seven-state transition diagram. We should also notice two diagrams which two states, that is a sleep in memory and sleep swapped. So a sleep in memory is a state that is a process which is in a blocked state. So whenever the process does an IO, it goes and gets blocked. So that is the reason it is. So this state corresponds to a blocked state, and from a blocked state, when the process is moved out, it goes into a state which we call as a sleep swapped. So if we just try to see this particular transition diagram, here we find a created state which is corresponding to a new state in 7-state transition diagram. Then ready to run in memory is ready state, is corresponding to a ready state. Then a sleep in memory is corresponding to a blocked state. Then sleep swapped is a blocked suspended, and ready to run swapped is ready suspended. So these are the states which we had seen in a 7-state transition diagram. Let us look on this side of the diagram. Here we find there is a state which is indicated as a user running state, and there is another state which is indicated as a kernel running state. So in a Unix system, what happens that the process could be running in a user mode. So when it is running in a user mode, it is in a user running state, and once the process can move from a user running state to a kernel running state with the help of a system calls. And once this is, and when a process moves from a user running state to a kernel running state by using a system call, it can return back once the required IO services are provided. It can return back to the user running mode once again, and from the kernel running mode, the process can move, can go and get preempted, and or the final state is indicated as a final state of a process is indicated as a zombie state. That is something similar to exit state in case of a 7-state transition diagram. Let us also note one thing here, that when the process is running in a kernel, process is in kernel running mode, and if an interrupt comes, we can see that the arrow returns back to the same thing. That essentially means that a process which is inside the kernel running mode, it cannot be preempted. So a kernel process cannot be preempted. So we find that Unix kernel is a non-preemptive kernel. At some point of a time, maybe because the process time slice has expired. When a user process was running in a kernel mode, its time slice got expired. So it might go to a state which is known as a preempted state, and from the preempted state, once again the process can go into a user running state. So this is how the Unix system operates. So if we take an example of a Unix system 5, we find that Unix supports two category of processes. One we call a system process, and other we call as a user process. System processes you would run in kernel mode, that is a kernel running mode, and system processes are used for performing the administrative and housekeeping functions such as memory allocation, process swapping, scheduling, etc. And user process runs in a user mode to execute the user program and utilities, and it runs in a kernel mode to execute instruction belonging to the kernel. That is whenever a user process would make a IO request, so the user process would change from a user running mode to a kernel running mode, and it will execute instructions which are belonging to the kernel. And usually the user process enters in a kernel mode by issuing a system call, or while a user process is executing, if some interrupts or exceptions occur, the process would move from a user running mode to the kernel running mode. In the Unix, process 0, which is also known as a swapper process, is pre-crafted, predefined right in the beginning, and this pre-crafted process is loaded at a boot time, and once this is loaded, then when it starts executing, this swapper process creates another process that is that has a process ID of a 1. So we say swapper process spawns a process 1, which is known as a init process, and init process acts as an ancestor for all other processes. So all other processes are created by the init process. Till now, what we have learnt about we would just summarize the process before looking at that how the process is organized in the memory inside an operating system. So what we have learned till at this point of time is process. We have seen a process. Process is an instance of executing program, and in multi-programming or multiprocessing environment, we find that a number of processes can reside in a system, and at any instance of a time, these processes which are residing in the system can be in different states, such as a ready state or new state or a blocked or running or ready suspended, etc. And the transition can occur from one state to another state, depending on a certain conditions inside the system. Processes, any process which is executing on a given computing system would use the available system resources, and once the process completes its job, it releases the resources which it was utilizing, and in fact, the OS operating system is responsible for managing all the processes in the system. Let us just take a diagrammatic diagram which indicates that how at any given instance of time how the processes are going to be there in the memory and how they would be utilizing various resources and services which are available. So in this particular example, we find that we have processes which are so 3 processes. We are saying P1, P2, Pn. These are 3 processes. We can see that the process P1 is holding processor, that is, it is executing on a processor. It is using some I/O device. So it is using a number of I/O device. So this I/O device is being used by process P1. This is also used by this, and the process P1 is using some amount of memory. So if we look at this diagram very clearly indicates that what are the resources which are available with the process P1. So process P1 in this case is executing on a processor, is having 2 different I/O devices, and it is loaded into the main memory. When we look at a process P2 has made a request for an I/O device which is currently held by the process P1. The dashed line indicates in this diagram that there is a request from a process P2 for a given I/O device, and a solid line indicates that the process is holding that particular device. So for a P2 we can say that it is waiting for an I/O device, and it is holding another I/O device, and it is loaded into the memory, and it is not running on the processor. The process P1 is running, but process P2 is perhaps it is not in running state, and the process nth process here we even see that the nth process is connected with the memory with the help of a dashed line, indicating that the nth process has yet not been allocated the memory. So that is we can say that nth process is currently in a kind of a new state where the data structure has been created, but no memory allocation has been carried out. So we have just seen that operating system manages the processes. So we need to see that what are the activities, what are the information which operating system as a process manager is required to have. So we can say that operating system must have information about current state of processes, that whether in what state a specific process is, and the current state of resources in the system. The computing system would have a set of resources. So your resources could be a processor, your resources would be files, your resources would be IO devices. So what is the current state of resources in the system? How many resources, how many devices are allocated to the processes, to which particular processes, number of opens files, all these information is required to be held by the operating system. OS must keep track of a utilization of resources by individual processes, that which are the IO devices being used by which particular process. OS must, so for OS to keep track of all these information, the OS must construct control structure or some kind of tables to maintain the information about each entity which it is managing. So OS as a process manager, what it tries to do is it tries to maintain several tables or several control structures. It maintains predominantly 4 types of a table. One can say that it maintains. One is a memory table. We will see other memory table, IO table, file table, and process table. We will see each of them, that what the information is contained in each of the table. So memory table keeps track of allocation of a main memory to a process, allocation of a secondary memory to a process. Some part of where we know that with load on demand memory management scheme, part of a process could be in memory and part of process could be on a secondary storage. So we would need to keep a track of allocation of a secondary memory to individual processes, and we would also need to keep track of protection attributes of a main and a secondary memory, and we would also need to keep track of the shared memory regions and the protection information. And it is also required to, we would also require to manage something what we call as a virtual memory. So the concept, we would introduce a concept of a virtual memory at a time when we start talking about the memory management. So that is what we what the OS requires. Memory tables, they keep track of these things. Then when it comes to the IO table would keep track of resource allocation, that what resources are allocated to what processes, and resource availability, and the pending request, what requests are coming from what processes. File table. So another important table is file table. File table provides information about files, existing file, and where these existing files are where these files are located on a secondary memory, and current status and attribute of a files, that would be in terms of whether the file is open or whether the file is archived, how many instances of file is open, etc. This information is kept in a file table. And then finally we have a process table, which in terms keeps track of all the processes. Diagrammatically, we can say that we have we have predominantly, as I said, that we have 4 types of tables. So memory table, process table, file table, and IO table. IO table would there would be a IO pointer which will be pointing to a IO table. Similarly, file file table, and processes would be processing to would be pointing to primary process table, where the number of processes would be there, where in terms each of the processes would actually be processing to what we call as a process image, the actual processes. We will see that what is the meaning of a process and process image. So, when we talk about a process image actually consists of the user data, the user program. Any process we've seen in our earlier discussion as well, that a process has a text section, that is a program, and then process this program would operate on a set of data. So, you have a user data, and then we have a system stack, and then there is something which we call as a process control block, and process control block actually contains the process attributes. We will define shortly that what are the process attributes which are contained, which must be contained inside the process control block. Coming to the process management, to manage or control a process, OS must know. There are two fundamental things that to manage and control the OS, control a process, OS must know where process is located and attributes of a processes. We will see that what those attributes are. For example, attribute could be a process ID, state, process state, etc. And the collection of these attributes, collection of process attributes are held in a structure what we call as a process control block. The process attribute, the set of things, the important things which constitutes the process attribute is process identification, the elements by which the process can be identified, then processor state information, that is while the process is executing on a processor, what is the processor state, and then finally process control information. When it comes to a process identification, three things are maintained. Identifier of the process, we should have some value, some identifier associated with each of the process. Identifier of the process that created this process, that is a parent of the process, and then user identifier, that who is the user who created this process. Usually the operating systems, most of the operating system, more so specifically about the Unix operating system, we find that there is a parent-child relationship exists. A process, every process, existing process would have a parent process. So, when the parent process is killed, it would be found that child process also gets killed. So, there is some kind of parent-child process relationship that exists. Processor state information, coming to that, what is the processor related information which is stored. So, we find that we would have a user visible register. Any given processor has a set of has a register file, and for example, if we take the example of a Pentium processor, we find that it has a set of user visible registers. There's registers which are say EAX, EBX, ECX, EDX, ESI, EDI, CS, DS, etc. Then another important category of registers which are special purpose registers, and they are known as a control and status register. For an example, program counter, which is a very important register, which helps in pointing to the instruction which is required to be executed next. Then whenever any arithmetic or logical operations are performed, flags are changed, and these flags are used for condition check and branching. And at any given point of a time, there would be a certain conditions which would have occurred, and that would get indicated with the help of what we call as a status register. And then another very important register is a stack pointer, which is essentially used for manipulating the stack. So there are quite a few registers which form the part of a processor, and as a part of a processor state information, operating system would need to maintain the information contained in all these registers. The process control information. Process control information, we find that operating system would need to keep track of a scheduling and a state information. It will need to keep track of a inter-process communication. It would need to keep track of a process privileges, and it would need to carry out the memory management, and it will also need to keep track of a resource ownership and utilization. So all these informations are contained inside what we call these constitute the process control information. Functions. So coming to the various functions which is performed by the OS kernel. So we can broadly categorize these functions in 3 categories. We can say that the category 1, that is functions pertaining to purely a process management. So under this category, the OS kernel is responsible for process creation and termination. It is responsible for process scheduling. It is responsible for a process switching, that is context switch, and it is also responsible for process synchronization and support of what we call as a inter-process communication, and it is responsible for management of a process control block. The another function, that is a memory management function, that is also performed by OS kernel, where OS is responsible for allocation of address space to the process. OS is responsible for swapping, that is whenever for a want of more memory, if process needs to be swapped out, then as a part of a memory management, the swapping operation is performed. And then we know that a given computing system would either be using a paging scheme, or could be using a segmentation scheme, or it could be using a segmentation along with the paging. So the strategy which is used for managing the memory is it comes under the purview of a memory management. Then another important function which is performed by the OS kernel, that is IO management. So we know that user processes are not allowed to execute the IO instructions directly. So whenever user process wishes to carry out some kind of IO operation, it uses some kind of a system call, and whenever the system call it uses, the user process moves from a user running mode to a kernel running mode, and inside the kernel running mode, the IO management is required to be carried out to manage the IO devices and the services offered by IO services which is offered by the operating systems. So as a part of IO management, we find that there are a few important aspects which one would need to worry about, that is a buffer management. We quite often we use the term buffering of data. We should understand that the buffering term in general is used wherever we have kind of two different kind of devices which are transferring the information, moving the information, transferring information. In that case, there is a likelihood, or there is a great likelihood that there would be a speed mismatch between a two devices. For an example, when we try to read a data from a keyboard or read a data from a hard disk and try to load it into memory, so we find that the memory access speed is going to be of the order of a microsecond or nanosecond, whereas the data which one would access from a hard disk is going to be of the order of millisecond. So in that case, if the data is required to be transferred from a hard disk to the memory, then the memory device would need to wait for a millisecond duration of a time, because hard disk cannot supply data faster than in less than a millisecond time. So that in such a situation, what happens that we create an intermediate buffer, where the information from a slower device is buffered into some kind of a memory, and then from this buffer it is transferred eventually to its final destination. So buffer management is a very, very important aspect in case of IO management. Then in general, we would require, when number of processes are there and these processes are going to make a request for varying IO devices, then the allocation and handling of a request is going to be a responsibility of a IO management module. And in addition to these three important modules which we have seen, there is something known as a support service module, which is essentially responsible for interrupt handling, accounting and monitoring of the system. Thank you.